Alright, let's take a look at Leetcode's 297 Serialize and Deserialize binary tree. Take note that this says binary tree, and then there's another problem, Leetcode 449, which is Serialize and Deserialize binary search tree. And let me just tell you real quick that there's absolutely no difference in the way that you're going to approach the problems. You can actually just copy the same code over, and it would work for both of them. And because the fact that one is giving you an input of a binary search tree makes absolutely no difference on how you're going to serialize and deserialize it. So actually, I'm not even sure why they made two separate problems, and actually one is even labeled a medium and the other one is labeled a hard, but just know that there's absolutely no difference in the way that you approach the problem. I guess I can kind of just explain why, but basically, the only difference between a binary search tree is a more specific version of a binary tree. And so the binary search tree has one property, which is that the left node has to be less than the parent node's value, and then the parent node's value has to be less than the right node's value. So that property makes no difference on how we're going to turn the root. So basically our task is to serialize and deserialize. So basically what serialize means is we're turning a tree into a string, and then deserialize is we're going to take that string that we just created and turn it back into the original tree. So the property of the parent-child's relationship with the left child and right child's relationship, that makes no difference. So just treat these problems as exactly the same. Okay, so let's see, how do we serialize this tree root that we're given into a string, and then how do we turn that string back into a tree structure again? So we're going to use a pre-order traversal. So if you're not familiar with pre-order traversal, maybe you should review that first. There's some problems on Leetcode. I think there's one literally called pre-order traversal of a binary tree. So that's probably a good first one to do, and you can do that the easy way. We're gonna do a recursive implementation of that, so that's even easier than the iterative. The iterative may be a little bit more involved, but still, either way, pre-order is easier than in-order and easier than post-order traversals. So, here's the pseudo code for it. Literally, if you forgot, but pre-order is just you're going to process the root first, and then you're going to process the left node, and then you're going to process the right node. So what you do here is you do the processing at this node, and then you traverse the left, and then you traverse the right. So if we were to be given a tree which looks like this, 2, 1, 3, 4, the output would be in the order of 2, 1, 3, 4. More specifically, if we were to include the null values, it would be 2, 1, and then null, and then null, and then 3, 4, and then the other side of the 3, the right side of 3 would also be null. So yeah, if we were to output this tree in a pre-order traversal ordering, it would look like this: 2, 1, null, null, 3, 4, null. And that's pretty much how we're going to create our serialized string. We're just going to traverse it in pre-order, and then use some delimiters like this. And yeah, to make sure we separate the values. So we don't want it to say like 3, 4 or anything. We want it to be each value to be separated by what it's supposed to be. Yeah, so okay, so the serialized version of this graph here is actually not 2, 1, none, none, 3, 4. Well, that's one way to serialize it, but the way we want to serialize it is actually 2, 1, none, none, 3, 4, none, 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 none. So I'll show you why we're going to do that in a second. We're basically just going to use these nuns, or I mean, in Python it's none, in other languages null, same thing. But basically you're using these nuns as barriers, and they'll be helpful when you later on when you're actually going to go and deserialize, aka building it back up. So okay, so let's see, how do we get all these nuns? So if we go in the preorder traversal, which is we look at the root, then we look at the left node, and then from here we look at the left again, which is none, which is null. So that's why I have 2, 1, 3 here. And then after you look at this null value, then you go back up to the parent, and then the parent has to go down to the right again. So that's why we get this other none. And then once that finishes, then you go back up to the parent, and then since 1 has finished looking at both left and right, then it goes back up to the 2, and then 2 still has to look at the right side, so it brings you down to the 3. So then that's why we have the 3 next. And then the 3 will go look at its left child first, and then that's why you have the 4 here. And then 4 will go look at its left, which is null, that's why you have the none here. And then goes back up to 4, and then goes down to the right, which is also none. And that's why I have the none here. And then it goes back up to the 4, and then 4 has finished looking at both left and right, so it goes back up to the 3, and then the 3 still has to look at the right side, which is null, and that's why you have the last null here. And then 3 is done, bubbles back up to the 2, and then 2 is completed as well. So that's how we get this serialized string here. And you'll see why it's important that we mark all of these nulls. And you'll see that when we actually build it. Okay, so that's the serialized function. So once you've serialized it, you will return this string here. And then once we're getting into the deserialized function, our input is going to be this string. So the first thing we want to do with this string is we're going to want to turn it into a deck. So a deck is basically just it's a doubly linked list in Python. You can think about it as like a list or an array where you can pop from the beginning and end in O of 1 time. So that's why we want to use it. We want that property of O of 1 popping from the beginning of the list, as we're going to be popping from the beginning, and you'll see why in a second. So we're going to just call this deck because we're going to turn it into a deck. And then also we're going to just, obviously we're going to split it by the delimiter so that it's an array. And then, yeah. But I'm not going to actually do that for the sake of this example and time. So, okay, let's see. So, alright, so how do we actually go from this string and turn it into the graph again? So, basically what's going to happen is we're going to have I'm gonna have the pseudo code here, and you can kind of just follow along and use it to reference how we're going to build out this graph. Okay, so the first thing you want to do at each iteration of this recursive call, let me just preface it by saying that the way that we deconstructed the tree into a string is the same way we're going to take this string and reconstruct it back into the tree. So we're going to use preorder again a recursive preorder in order to turn it from the string back into the original tree. So how do we do that? I mean, it's pretty much the exact same thing. You do the processing, which is, in this case, instead of printing, we're going to be creating a node with the value. And then after you create the node, then you will traverse the left and then traverse the right. And so here, basically, we're going to just be setting the nodes. So the node that we just created, we're going to set that node's left value. We're going to assign it to this recursive call, and each recursive call is going to return a node, so that's why you can assign it to this recursive call. Same thing for the right child of the node that we just created. Okay, so let's walk through this code and see how that actually takes place. So first thing we do is we're going to take this node. So just ignore this base case here. This is basically like a base case slash edge case, and I'll get to this in a second. But just kind of ignore this, visually ignore this. First thing we do is we're going to take the first element in the deck, the leftmost element, and we're going to use that value to create a node. So we're going to create a node with value 2, right? That's why we have node here, node 2 at the top. I'm going to just delete all this and show you from scratch. So after you use this value to create the node, then you pop it off from the deck. I already popped it off. I just deleted it, right? And then this node's left value is going to be assigned to the build function. So whenever we call a function, we're kind of just like sidetracked. So we're going to get sidetracked into this build function. And like I said, just ignore this base case for now. So let's see what happens when we're in this build function. This is the second time we're in the build function. The first time we created this too. So now let's see what happens. Then we're going to come to this condition here. So we're going to create another node using the first element in the deck. What's the first element in the deck? It's a 1. So I'm going to use that to create a new node of 1. Let's just put it here. So these two nodes are not connected yet. They don't have any relationship with each other yet. They will be connected later on when we hit the return statement. And I'll show you I'm kind of just going to walk through it the way the computer would walk through it. So at this moment, these two nodes do not have a relationship with each other. They're not connected yet. They're kind of just floating around in space. And I'll show you the exact moment when they get hooked up. Okay, so right now it's just a free floating node of value 1. And then once you hit that node 1 and then you pop it off the stack, what do you do after you pop it off? Then you create another left node using this build function. So we hit the build again, and then now you are in the next build iteration. And then so now this is when the case is actually going to be hit. So now you can stop ignoring this, and now you can take a look at this this conditional logic. So it says that if the leftmost item in the deck is equal to none, then you can actually just pop it off and return none. So this left node, we've actually just created this as none, and we've returned it already. So now we can safely say that these two nodes have been connected. This build has actually already returned the value of none to this left. And then same thing is going to happen after you finish that. Then the next line of code, so we're actually going back to the call stack, which had this for the call stack for this node of value 1. So the node of value 1 just finished this line of building the left node. Now it's going to build the right node, and the right node is going to have the exact same result as what happened in the line previously for the left node. It hits this new build function, it goes into the build, and then it sees that the leftmost, sorry, I need to delete this. It sees that the leftmost, which is also a none, so it's going to pop that off, and then it's going to return. So it returns right here. So that none value gets returned here. So the right side, this one's right side also gets created right now immediately. Okay, so but the 2 and 1 have not been connected yet. It's just these two have been connected. And just if you guys already know pre-order traversal, you can I've already kind of just given this whole spiel of what we're gonna do. But if you're not too familiar with how the depth first search recursion is going to actually take place, then you can continue to follow along, and I'll walk through step by step how everything's going to be connected together. Okay, so after you finish that statement here, that null, so this one, the call stack for the 1 just finished building the left, and it just finished building the right. And then now what's the next statement, next line after that? It's actually going to return this node here. So it's going to return itself to the previous call stack. So which call stack was the one that started this whole subtree? It was the call stack of 2's left. So recall that this one's left child, so the node.left equals build, that build was the one responsible for building all of this. So now this left child is going to be assigned. So finally this 2 is being assigned, this 2's left child is being assigned to this whole left subtree. So that's kind of how you can see depth first search. It kind of bubbles upwards from the bottom to the top. That's how these things get hooked up, from the bottom to the top. Okay, so then we finished creating everything on the left side. Now, so we're back at the original call stack of for the node of value 2, right? It just finished assigning this whole left subtree to this statement of node.left equals build, right? So we just finished this statement. Now we're going to do node.right equals build, and then build is going to start, now we're going to continue, we're going to keep on getting sidetracked again and again by building and building over and over again. So you'll see. So we hit this build statement, and then we go into build, and then so now we can ignore this statement. So node equals, so now that we're in a new build statement, we're going to create a node, and that is going to be whatever is the leftmost on the deck, which is the 3 here. So we're going to just create a floating point of 3 somewhere in memory, because this 2's right value has not yet been assigned to this subtree starting with 3, right? It has not been assigned yet. We've been sidetracked by calling this build method, and the build method created a new node of value 3, and then we're going to pop it off the stack or deck, and then we're going to, we're in this node's call stack, and then so this node is going to hit this line, node.left equals build. So this node is going to hit the build, and then let's see what is it going to do in that new build sidetrack. We're going to get sidetracked again, and what's going to happen in this new call to build? It's going to create another node using the leftmost item in the deck, which is 4. So it's going to create a floating node of value 4 somewhere in memory, and then after you do that, then it's going to call the left node.left again with build, and then let's see what happens in this call stack for build. So now we can hit this case again where the leftmost is none, so we're going to just pop that off and then return none. So that returned us back to the previous call, node.left equals build, right? So now we can safely say that 4's left value is none. Yep. And then, so after 4 just finished creating the left side, now 4 is going to hit this next statement. So 4 just finished this statement, and then 4.right equals build. And then what is this new build method going to take us to do? It's going to do the same thing. It's going to see that the deck's value is none, so it pops it off and then returns none. So now 4's right side has returned none. So this node.right has returned a value of none into 4's right. Okay, right? So now 4 just finished doing all of these pieces of logic, right? 4 just created the left, which is none, and the right, which is none. So it's going to hit this statement, which is return node. So it's going to return itself to whatever call stack it came from. So the call stack that it came from was 3, the call stack of 3, right? When 3 called 3.left equals build, that's what created this whole subtree of 4. So that's when it's going to assign this subtree here to 3's left side. And then so 3 has just finished the call stack for 3 has just finished this node.left, and then now it's going to go on to the next statement, which is node.right equals build, and then it's going to see that build equals it's going to go into the new a new iteration for build, and then it's going to hit this condition, and it sees that the leftmost item in the deck is none, so it pops that off and then deletes it and then returns none. So now this node.right just returned a value of none. So we can safely say that this 3, the 3's right value is none. And then yep, so now that 3 has just finished all of the statements here, so it just finished building the left, and it finished assigning the left and the right. Now it can just return itself, right? Return this node, which is itself. So which call stack did this 3 come from? This 3 was created as a result of when 2 called the build function, right? When 2's right side did this whole statement here, and it carried us off to create this whole tree. So this is when 2's right side gets assigned to this tree starting with 3. Okay, so that's kind of a walkthrough of how this whole pre-order traversal creation happens. It's a little bit tough to understand the first time, so if you did not understand that, please, go back slowly, watch it again. I tried my best to explain it. I'll have the code in the description on GitHub, and this pseudo code that I walked you through is essentially exactly what's going to happen in the actual code down here. There's literally no differences in this. So hopefully, you can understand how these 4 lines are so powerful to create, this whole tree structure recursively. Yeah. So hopefully now you can understand how to turn the original tree into a string, and then that string back into the tree using pre-order traversal both ways. So try to implement the code yourself first for both these questions. It's the exact same, and if you get stuck, reference my code. And good luck. Thanks for watching, and please leave some feedback. Please tell me if my teaching was terrible or whatever the case. I'll try my best to improve, try my best to make these shorter. This was a really long video, so I'll try my best to condense them next time, try my best to be very well prepared with what I want to say. It takes a lot of effort, honestly. I have to, write an outline and stuff if I were to really try to be as time efficient as possible. So hopefully you guys, hopefully you guys enjoyed this. And alright, thanks for watching.